Hi y'all, welcome back to another round of physics. And today, as promised, we're still going to be dealing with motion, but the idea is that we're going to be dealing with the algebraic equations now. Equations. And namely, I'm going to give you a couple different ways that you can derive these equations, and then we'll spend some time practicing them, just some straightforward or simple applications. Now, as promised, as you get better at this, please be aware that once you master this idea, then you'll be able to transition hopefully to 2 or 3 dimensions without much of an issue. It's just simply taking the problem and breaking it into its individual x direction, y direction, z direction, and then going at it. So to get started for today, I'll point out that we're going to try to we're going to build equations that are relating our changes in position, our initial speeds, maybe our final speeds, acceleration, and time. These are generally the variables that you will see in what we call the kinematic equations. So kinematic equations. In other words, equations describing motion. Now, as a forewarning, and right away I'll let you know, these equations are only valid in a very particular sense, and that is when the acceleration is constant. So we have to be very careful already. We're running into a restriction. Acceleration must be constant. If your acceleration is not constant, then you cannot apply these kinematic equations. And I can't tell you how many times I've seen it where somebody sees something, says, oh, I've given position and speed, I must, and time, okay, well, I can just apply a kinematic equation and going at it. And they don't realize that if your acceleration is non-constant, then you can't do that. Okay? So you are forewarned, this is the restriction for the equation. Acceleration must be constant. And you say, well, why are we spending time with this specific case? And I'll say right away, one of your natural experiences with physics since you were, before you learned how to walk, was falling. That's one of the experiences that we've been built in and experienced all the time. And when we fall, free fall is a constant acceleration problem. And so even from the various early ages, we were used to free fall and constant acceleration. It just makes it easy to deal with. It's something to study as well, but it's widely applicable. So falling, objects sliding across floors and stopping, maybe hitting the brakes on your car, that tends to be a constant acceleration. So there's a lot of places where this does apply and it can be rather useful. So that being said, we're going after some algebraic equations here. Let's go ahead and get rid of this. And I've already mentioned that acceleration must be equal to constant. Why don't we spend a second and get an idea about what is it about this restriction that allows us to actually form the equations. And the name idea is actually when acceleration is a constant, we can introduce the arithmetic average. Arithmetic average. You say, what the heck is that? And simply put, it's the average that you're usually dealing with or that you're used to dealing with. If I said something like, what's the average of 1 and 3, in your head you're probably already going, okay, it's 2. Yeah, of course, what you're doing is actually the arithmetic average in your head. What you've done is you've said, okay, well, to find the average, I take 1 plus 3, and then I divide by the number of numbers I have. I have 1 and 3, that's 2 numbers, so this must be the average. So you add 1 and 3, divide by 2, and that's how you end up with 2. Now, you might not have actually gone through that whole process. You might have naturally just said, oh, it's 2, that's it. But this is the way that you could actually go through and find what we call the arithmetic average. Now, in the case at hand, what we're dealing with is not, well, they are numbers, but really what the arithmetic average, where it comes into play, is when we're talking about the velocity or the speed of the object. And here, let's take this and explain what's going on. So let me drop this in right here. Let's move it out of the way. And what the arithmetic average does for us in this case is, say I have a velocity, and I'll draw a line then. Say I have a velocity versus time that looks like a straight line. What the arithmetic average allows us to do is, rather than thinking about a velocity that's changing And you notice the change is constant, the slope is constant, the velocity is linear. What the arithmetic average allows us to do is, this is the physical situation, a changing velocity with time. But what we can model that as, because it's a linear velocity, is we can actually model it not as a linearly changing velocity, but rather as a constant velocity, like this. Oops, let's put the line in, like this, where it just goes constant all the way out to the time. You say, well, what allows us to do that? That's the arithmetic average. And what's really going on here, what makes it work, is the fact that if I look at the area of this entire triangle and I compare it to the area of this rectangle, we'll find out that the two areas are the same. In other words, even though this is my physical situation, I can model it like this, and all of the important quantities, position, average velocity, acceleration, all of those important physical quantities are the same in those two situations. So what ends up happening is when we apply the arithmetic average, we're taking this linear velocity and we're modeling it as a constant velocity. And then we can go through and do our equations. That's the key, the absolute key. And again, you see why. If the acceleration is constant, then your velocity is linear. And then through the arithmetic average allows you to model it as a constant velocity. That's kind of the process. Okay? Let's go ahead and get rid of all that. So let's get rid of that. So how do we actually use this? I'm going to do it two ways. So the first way that I'm going to derive these equations is I'm just going to do it algebraically. So in other words, you don't have to have any calculus. You can just sit down and hammer through this, and it should make some sense. And so what I'm going to start off with is actually the definition of the average acceleration. So your average acceleration is defined as the change in velocity per unit time. And now I'm going to introduce a second idea, and that is the average velocity, vg. You have actually now two expressions for this. The first one, delta x over delta t, which you all know and love. And the second one is the arithmetic average. So right here, when I write this down, v final plus v initial over 2, now I'm using the arithmetic average. I am assuming, this assumes a is equal constant. If I use this equation at any point, I am making that assumption. Now let's see what we can do. The first thing I'm going to do is I have a delta symbol. I'm going to start here on this equation. Okay? And I have a delta symbol. Okay? And so what I am going to do is I'm going to expand out that delta symbol. So I'm going to have, so I'll put a, and I'm going to put delta t on this side. So rather than having to write out these fractions, I'll move the t to the other side. And I have v final minus v initial, v naught. Now, I'm going to go ahead and get rid of v final. That's what I want to do in this expression here. And so the first thing that you notice is that I have another equation given by the arithmetic average that contains v final. So what I'm going to do is I'm going to take this equation and solve for v final, step 1. So I get 2v average minus v naught is equal to v final. So you notice I multiplied by 2 and I subtracted the initial velocity. So I'm going to substitute that in. I'll substitute that in to this equation. Substitute. And so I have a delta t equals 2v average minus 2 v naught. I have one v naught, the second v naught, so now I have 2. You say, well, did that really get us anywhere? Not yet. But now we'll use our third equation, the one in the middle here, that gives us v average and its relationship to the change in x. So now I'm going to take that and substitute it in right here. Okay? And I don't have to do any arranging or anything. I'm just going to do a straight substitution. So I end up with something that says a delta t equals 2 times delta x over delta t minus 2 v naught. And now the last thing I'm going to do, because this is how your book presents it, this is done. We have a relationship. We don't need to go any further. We have times, changes in positions, accelerations. I'm going to rearrange it because this tends to be the standard format that it's presented in. And so what I'm going to do is I'm going to get delta x by itself. So the first thing I need to do is I'm going to add this to the other side. So I have a delta t plus 2v naught equals 2 delta x over delta t. And now I'll go ahead and multiply everything through by delta t divided by 2. So if I do that, I end up, I'm going to swap the order here, I end up with v naught delta t, so the 2 cancels the 2, plus no 2 in front here, so I have 1/2 a delta t squared equals delta x. And this is one, this is one of the kinematic equations that you'll often see in a textbook. And change in position equals v naught delta t plus 1/2 at squared. Okay. So there's one of them. Now you say, wait a minute, Greg, why did you get rid, when we go back up here, why did you decide to get rid of v final? And I said, arbitrarily. Notice that down here, of those 6 quantities I gave you initially, or excuse me, 5 quantities, I said, I gave you delta x, I gave you v naught, I gave you v final, a, and t. Of these 5, you could think of it as 6 if you expand the delta. Of those, the one that is no longer in this final expression is the v final. If you would prefer to derive an equation that is missing v naught, it will contain v final in it. And well, shoot, I guess it comes in right here. If you want a different equation, instead of substituting in for v final, we could solve for v naught instead. So then you have something that says 2v average minus v final equals v naught. You can do the substitution. You can run the same song and dance. Pretty cool. In fact, let's just run it real fast. If you run the same song and dance, I believe that the only thing that changes is right here. So if you did this substitution, I believe your final answer, your final equation, is going to be delta x equals minus v final delta t plus 1/2 a delta t squared. And go ahead and check that. I believe that this is right. Now, generally, this kinematic equation generally isn't quoted in textbooks. It's very rare that I see that, but it can be done. Okay? So this is something else that I'll warn you about, is it's nice to know where the equations come from. Okay? Not only does that help you remember what assumptions are made when you go in and actually do the equation or use it, but it also helps because sometimes you won't have the equation in your textbook and you need to derive it. You say, well, shoot, I don't know the initial speed, but I know the final speed. But this book doesn't give me that equation. Sometimes that helps to know where the equations come from, and then you can build it. I'll say you will not get paid in the future for looking up an equation in a textbook. You're going to get paid for building the equation from scratch. Just tell you that right now. Okay. So this is, we'll call this the first kinematic equation. And I guess we could call this, you know, the first one. We could call this 1b, something like that. Okay. Let's go ahead and I will get rid of all of that. Okay. And we'll go a slightly different way here. So rather than deriving an equation that doesn't have a final speed or an initial speed, let's go ahead and build an equation that doesn't contain delta t. Okay? So you notice already, let's go ahead and move the delta t over. So I have, I'll swap the a and the delta t. So I'll have delta t is equal to delta v over a. And I'll do the same thing right here. So now I'm using this one, and I'm using this one. I have delta t is equal to delta x over v average. And now since I have delta t equals and delta t equals, I'm going to set those two equations equal to each other. So I can write delta v over a equals delta x over v average. I'm just taking those two and merging them together. Now, let me expand out the meaning of delta. So I have v final minus v initial over a equals delta x. And here, again, you know what I'm going to do. I'm going to take my arithmetic average and substitute it in right here. So I will have v final plus v naught, I guess compound fraction, over 2. Now, let's go ahead and rearrange to get rid of all the fractions. Okay? So I will end up with something over here. I'll have v final minus v naught times the quantity v final plus v naught equals, move the a over, and then I multiply, well, I move the a over, so I get a delta x. And then right here, you notice I can write 2 over 2. The 2 here cancels that one, and so I must end up with a 2 in the numerator. Lastly, let's go ahead and FOIL this. And if you know, for example, if you have two of the same terms and it only is a difference of a negative sign, that means that the inner two are going to cancel out. So if you FOIL first, you get final squared. Out last, you have negative v naught squared. And then if you do the inners, let's see, negative v naught v final, and the outers v final v naught, you notice that those two will cancel each other out. So this is the end, equals 2a delta x, right here. And that's another kinematic equation. I'll put down a second kinematic equation too. Okay. Now notice here, the thing that's not included in the equation is delta t. As promised, when you're dealing with a kinematic equation, there's always one term that's not there. Okay. So in this case, it's delta t. The past one, it was v final. You could say, well, where are the other kinematic equations? Some of them are the definitions that we've been using. So here's one. Acceleration, v final, v initial, delta t. This one's missing the delta x. Okay? Or if you prefer, another one is right here. Right? If I combine, I guess I should probably, let's go ahead. There's one right there. Let's go ahead and find the last one. The last one can simply be found by taking the definition of the velocity, average velocity, and the arithmetic average. And if we plug those two together, you get something like delta x, say 2 delta x is equal to, yeah, you see, v final plus v naught delta t. Kind of boring, right? I mean, this is just delta x is equal to your average speed times your time. Okay. So this one's missing delta x, not there. This one, acceleration, not there. Okay. So to summarize for you, let's go ahead and write all these out one last time so you can see all of them in their full-blown glory. So I said, okay, well, one of them is delta x equals v naught delta t plus 1/2 a delta t squared. I said one is v final squared minus v naught squared equals 2a delta x. One of them is a is equal to, I'll write it out in longhand just so you can see it, v final minus v naught over delta t. And we said that one is delta x is equal to v final plus v naught over 2 delta t. So I think that's pretty much covers it for the algebraic derivation of the kinematic equations. I'll save the derivation using calculus for the next video just to keep everything time-wise a little bit more brief. So thanks for your attention. We'll see you next time.